So the transfer function of the PI controller is the 1 upon 1 plus kp into 1 plus 1 upon tau is. ओके सो ये हमने ट्रांसफर फंक्शन डिफाइन कर दिया कंट्रोलर का, सॉरी हाँ यस कंट्रोलर का, जीसी इज द टाइम ट्रांसफर फंक्शन ऑफ कंट्रोलर. So you can see this is controller, this is the PI controller, okay, and then this is the plant is 1 upon s plus whole cube, and then the feedback, okay, this is the, और यहाँ पर सिचुएशन पॉइंट था, दिस इज लीनियर तो इसको हम ले लेंगे नहीं, ओके. तो PI controller, the transfer function of the PI controller is GC, or this is the gain, okay. So overall and the feedback is 1, so G underscore C is क्या हो जाएगा, फीडबैक GC, G into GC, ये हो गया आपका फॉरवर्ड पाथ, G into GC, and the feedback, this is, there is a 1 unity feedback, so we have represented here G underscore GC in the forward path, and the feedback path is 1, so forward and feedback, it will give the transfer function overall system G underscore C, okay. And the value of tau I, 1 upon 1 plus 1 upon tau is into kp, okay. So what will the kp, we have to choose two value, first the variable is the kp and second the tau I. So we can see here in the previous example, the value of kp, okay, you can see here, yes, you can see in the picture the which value of the kp is going to give the best result, you can say optimal result in all these value. So you can see here the kp equal to 1 will producing the satisfactory results as comparison to others. So we have fixed the value here, okay, we have fixed the value kp is equals to 1 here, the transfer function of the system is defined here, okay. So just we have taken s, what is this, s is the Laplacian operator, right? So now you can see tau I is, now we are going to vary from 0.7, just we have taken, you can take any value 0.7 to 1.5, okay, by varying the step change is 0.7, 0.8, 0.9 and so on. The step change is 0.1 we have taken here, 0.7 to 1.5, and we are varying with the step change is 0.1, okay. So this is the for loop, you can simulate the system, okay, like this, okay. So now you can see here the response of the system by varying the different value of the tau I, okay. So when we zoom this picture, okay, so this such type of response will come, okay. So you can see the value of tau I, as we are increasing, the oscillation is going to diminishes, okay, and the best response will come at, you can say, at tau is equals to 1.5. However, the value at the value of tau is equals to 0.7, you can see the response is highly oscillatory, okay. So as the tau I is increasing, the oscillation will decreases. So you can say that the value of ki is increases, the oscillation will decreases or increases. What will happen? As the value of ki increases, the oscillation is decreases.
Yes, oscillation decrease.
As tau I is increases, the value of oscillation is decreases. Tau I increase करेगा, and the relation of ki is with the tau I is reciprocal. So ki increases, the oscillation increases. Now I'm coming to the PID. We have seen the PI controller response. सो पहले हमने क्या किया, हमने प्रोपोर्शनल कंट्रोलर से पहले एक वैल्यू फिक्स कर लिया, देन वी हैव choose the value of integral ki tau I value, okay, and then we are changing the value at, let's say we have choose the value of kp is equals to 1, tau y is equals to 1, okay, and the transfer function of the system is like this, okay, and now we are varying the value of tau d, okay, tau d is varying from 0.1 to 2, okay, with a step change of 0.2. You can take any value. I have taken this value, okay. So this is a standard I will just have taken, okay. The GC is equals to, now what is the transfer function of PID? I believe that you don't know. So just I am telling you, KP into 1 plus 1 upon tau IS into tau DS. So this is the transfer function for the PID controller. So it is written here, okay. So the value of tau I and tau KP is already defined in the above everywhere, okay. So now just we have take the feedback, okay, the transfer function, just feedback G into GC, because the controller transfer function is this one GC, okay, and the plant is 1 upon 1 plus S, 1 plus 1 Q. So we have G is already defined here, G is already defined here, just you put it here, G into GC, or 1 is in the feedback, 1 is the unity feedback, so we have taken 1, the unity feedback system. Take the step response, hold this value, hold all these pictures, and you want figures. So just you can see there the result, okay. So you can see as a tau d value is increases, okay, the response will come like this, okay. So it means the best response, you can choose the best response from by choosing the optimal value of this value, okay. So ये पिक्चर से आप उसको सेट कर सकते हैं. Now come to the next part, that is the in practical application the pure derivative action is never used. I already told why, due to the derivative kick. Why the derivative kick will come in the picture? It is due to the step response. Step response, d by dt of response step response gives the
Impulse.
impulse, and that is the undesirable or the noise amplification, okay. So it is generally we are using the derivative controller with the help of the first order low pass filter, already I have told, okay. This is the basic structure of the derivative controller. So now if you want to define such type of controller in the MATLAB, so you must be define the value of n also, okay. So the value of n is also defined like this one, okay. The whatever the code is like same, the code is given just to record the response. Find here the error is also recorded in the picture, so you can see here, okay, this is the the reference line, okay, and now we want to the value of n is chosen as 1, the best value, okay. The response is coming like this, just to record it, okay. Now you want इसको करके देखिएगा तब पता लगेगा आपको, है ना, okay. So this
Yes.
error is coming like this one when the value of n is 10, okay. Now come to the next, that is the very important. Wait a minute. See the video. This
Yes,
video is
so
very important.
the best way to find the gains for your PID controller are to derive the equations of motion of your system and then use systematic methods from linear control theory to find good choices of the gains. Now, often we can still design a good PID controller even without a good model of the system. And the way we do that is doing empirical gain tuning. So we're going to try an example of that right now. So first you might want to choose some reasonable gains for your system based on how much control effort you know is available and how much error you can expect to have. So we're going to start with some reasonable gains, but first let's take a look at our system over here. This yellow line represents what we're trying to control. Maybe it's the position of a robot arm.
Hello.
This white line represents our reference signals. So initially the reference is 0 and then it jumps up to some value and stays constant. That's called a step input to our controller, and therefore what we're going to be looking at is the step response of our controller. So this is a simulation written in MATLAB. Let's try some gains for this unknown system. So PID tests, and I'll start out with a negative value for my proportional gain, 0 for the integral, 0 for the derivative. And if I have wires to the motor hooked up backwards, for example, maybe I need positive gains, maybe I need negative gains. So this will just be a test to see whether I need positive or negative gains. So I press enter, and you can see here that the response of the motor went the wrong way. It's not going up, it's going away from the desired value. So that means I need positive gains. So let me try again with a value of 1 for the proportional gain and 0 for the integral and derivative. And now we can see that the output rises closer to the reference value, but it's still not doing very well. So this is my first guess. I'm going to mark that with a 1. So this is my K sub P axis for proportional gains, K sub D for derivative gains. And my first guess here was at K sub P equal to 1, K sub D equal to 0. Since I'm still far away from my desired value, I need to increase my proportional gain. So let me raise it to 10. And now you can see that we're coming closer to the desired value. So this is my guess number 2. But we're still pretty far away. Let's try increasing it by another factor of 10. Okay, now we're getting closer, but we still have a lot of ringing and overshoot here, so let me mark this as guess 3. For the heck of it, let's try increasing the gain by another factor of 10. Okay, and now we're not getting any improvement in behavior. And in fact, if we took a look at our control signal, we would see that because we have such large gains for K sub P, that the control signal is always saturating. It's always at its maximum or minimum limit. So we're getting this kind of strange looking behavior here. And that says we've probably gone too far just in the K sub P direction. So let's backtrack a little bit and try adding some damping. So we'll reduce our proportional gain to 100, make the derivative gain 1, and I see that. There's not much of an effect, so this is guess number 5. Let's try increasing that by a factor of 10. So we're going to increase the derivative gain by a factor of 10. You can see it damps out a little bit, but still not very much. We're getting a lot of oscillation and overshoot. Let's increase by another factor of 10. Okay, now we're starting to see more damping. It's still oscillating a little bit, so that's up here. Let's try increasing the damping by another factor of 10. Okay, now we're getting something that looks pretty good. So we're getting this smooth rise and settling. So this is guess number 8. Okay. So this response doesn't look bad. We still have some steady state error. Let's try increasing the stiffness and increasing the damping together, hopefully thereby keeping the good shape of our response, and this is called the transient response, while hopefully reducing this steady state error. So I'm going to double both the proportional and the derivative gain. So K sub P is 200, K sub D is 2000. Okay, now I'm getting even better performance, still the good transient response, less steady state error. So this is guess number 9. We've increased in both K sub P and K sub D. So let's stop there with our PD gain tuning. And by the way, we can't make our gains arbitrarily high or else we're going to see chattering behavior. Now let's try adding a little bit of integral action. So let's start out with Ki is equal to 1. So keep P and D as they are. And if you notice here now, the response starts slowly heading towards the desired steady state value. So we're seeing some effect of that K sub I. Let's increase by a factor of 10. Okay, now we're seeing that we're getting essentially zero steady state error, but we've introduced a little bit of overshoot. And that's what integral gain will do. While it tries to reduce steady state error, it may induce some instability. And if we wanted to emphasize that, we could increase that gain to 100. And now you're seeing lots of overshoot and oscillation. So we've gone too far with K sub I. So if we go back here, it looked like 1 was pretty good, looked like 10 was pretty good, but maybe somewhere in between. Let's try 5. And now this is a nice looking response. We get the zero steady state error fairly quickly, and there's no overshoot. So things you care about in your response are how much steady state error do you have here, and do you overshoot, and how long does it take to settle? So here it settles to, say, within 2% of the final value by around here or so. So the faster that happens, the better. The less overshoot, the better, and the less steady state error, the better. If you're working with a second order system, like a force controlling a mass, it's almost always best to start by tuning the proportional gain and then go to the derivative gain, and to save the integral for last. Again, it can have a destabilizing effect, so you have to be careful with its use.
So hope you understand the tuning with the help of the empirical gain tuning, or you can say the hit and trial method, right? So
Yes, sir.
in the next class we will start with the Ziegler-Nicholas method.